You plug your phone in at night, and by morning, it's at 100%. A few hours of scrolling later, it drops to 20, then 5, then the screen goes black. We tend to think of this as electricity simply leaking out of a container, but that is not what is physically happening inside the casing of your phone. Batteries are active chemical engines. As you use your device, the internal chemical reactants are consumed to push electrons through the circuit. As those chemical concentrations drop, the raw physical power the reaction can generate drops with them. That percentage on your screen is a live, real-time readout of a decaying chemical reaction. To measure that decay, we have to start at perfection. This photograph shows a vintage chemistry lab, the exact kind of rigid environment where scientists measure the standard electrode potential. This is the baseline theoretical power of a battery measured under flawless conditions. Achieving this standard measurement requires strict rules. The room must sit at exactly 298 Kelvin, or 25 degrees Celsius. Any gases must be at exactly 1 bar of pressure. Most importantly, all chemical ions in the solution must be mixed to exactly a 1 molar concentration. But your pocket is not a controlled laboratory. Step outside on a freezing day, or let your device run so the internal concentrations shift away from that perfect 1 molar mark, and that standard laboratory measurement becomes useless. In the late 19th century, German physicist Walther Nernst recognized this gap between theory and reality. He developed a mathematical tool to calculate the exact true voltage of a cell under any shifting, messy real-world condition. That reality patch is the Nernst Equation. This diagram outlines the full Nernst Equation. Its main goal is to calculate the true real-world cell potential, written as E cell. To find it, you start with the ideal lab voltage and subtract a modifier. That theoretical starting point is E naught cell. It is the baseline voltage measured under perfect lab conditions, usually pulled straight from a standard data table. To adjust that perfect number, we look at the variables on the right. The letter N stands for the exact number of electrons transferred during the chemical reaction. Q is the reaction quotient. The reaction quotient is a ratio that compares the current concentration of the chemical products to the remaining reactants. Look at this diagram of a water tank. A fully charged battery is like a tank filled to the brim. The massive volume of water, representing the reactants, pushes down, creating a high-pressure stream. That high pressure is your maximum voltage. As you use the battery, water flows out. The reactants are consumed, turning into products. The ratio, Q, grows larger, and the physical pressure driving the water drops. Because we mathematically subtract this growing Q block in the equation, an ever-increasing amount of chemical products guarantees your battery's power will continuously decline. Let's test this with a standard board exam scenario. This layout displays a zinc-copper cell where the concentrations are completely unbalanced. The zinc ions sit at 0.1 molar, while the copper ions are packed in at 1.5 molar. The breakdown begins with step 1, finding the standard potential. We subtract the anode's reduction potential of negative 0.76 volts from the cathode's positive 0.34 volts. The perfect lab baseline is exactly positive 1.10 volts. For step 2, we write out the overall chemical reaction. Zinc oxidizes and copper reduces, transferring exactly 2 electrons in the process. Our N value is 2. In step 3, we calculate Q by dividing the zinc products by the copper reactants. We only use the aqueous ions here. Pure solids have an activity level of 1, so we completely ignore them in this step. 0.1 divided by 1.5 gives us a Q of 0.0667. Step 4 brings it all together. We take our baseline of 1.10 volts, subtract the standard constant 0.0591 divided by our 2 electrons, and multiply it by the log of our Q value. The math resolves to a final calculated real-world voltage of 1.135 volts. Notice the result. Because the concentration of copper reactants was artificially high, the real-world battery generated more power than the perfect lab baseline. Calculating the messy reality gives you the true capacity. Eventually, that chemical capacity completely runs out. When your smartphone screen abruptly cuts to black, the physical battery inside hasn't just magically vanished. The internal chemistry has simply hit a state of perfect equilibrium. The forward reaction creating power and the reverse reaction consuming it are happening at the exact same rate, canceling each other out. Watch the equation change as equilibrium sets in. The real-world cell potential drops to absolute zero, allowing us to rearrange the remaining variables. The result is a new formula where standard cell potential equals 0.0591 over n times the log of Kc. This rearranged formula allows chemists to calculate the incredibly complex equilibrium constant using only basic standard lab data. They can predict exactly when a battery will die, completely bypassing the need for expensive physical experiments. On exams, avoid these 3 errors. Never subtract cathode from anode, never include pure solids in Q calculations, and always double-check negative signs with logs. The Nernst equation is the foundational law that dictates the decay of every electric vehicle and portable screen on Earth. Which calculation step in this formula confused you the most? Let me know in the comments. Next, we will cover Kohl-Rausch's law and connect these concepts directly to molar conductivity. Mastering the hidden math of physical chemistry is the absolute best way to truly understand the visible world.